Thank you, Adam. Okay, so in the past 2 lectures, it's not been too long, you saw that I defined twistor space for you. Let me recall that. And today onwards, we'll basically focus on various applications of twistor theory that have emerged since the 80s. So today, in the first lecture, we'll do the 80s. In the next lecture and the next lecture, I'll do applications of celestial holography. And if that doesn't carry over to the 6th lecture, I'll try to do some applications to deriving scattering amplitudes using twistor string theory. So today I just want to focus on the simplest application of twistor theory, by which you can study solutions of linear field equations on space-time in terms of certain holomorphic data on twistor space. So, and basically, just for intuition's sake, you can keep in mind the idea that this is analogous to going to Fourier space, where you have linear field equations, and a Fourier transform basically turns into an algebraic equation. The situation will be very similar here, where we'll take linear field equations like the Klein-Gordon equation, and we'll go to twistor space and get some basically free algebraic data that will encode a solution of that PDE. So let me remind you what twistor space was. Twistor space, or projective twistor space in strict parlance, is defined as the set of scaling equivalence classes of twistors mu alpha dot lambda alpha. So a pair of 2 spinors of opposite chirality, such that the last 2 components are not simultaneously 0, up to the usual C star action that I defined last time. S and C star. That's my twistor space. I'm going to develop a correspondence between some holomorphic differential forms on PT and solutions of linear field equations on complexified Minkowski space. And once you have a complex analytic solution, you can of course restrict to a real Minkowski slice by just taking the t, x, y, z coordinates to be real. Okay, so before I discuss how to get to this holomorphic data, I should first discuss what equations I'm going to solve. So on C13, you can have fields of various spins. I should say solutions of massless linear field equations. I forgot to write massless, but I'm going to deal with massless spinning particles. Every massless spinning particle in Minkowski space has 2 helicity degrees of freedom, except for a scalar. So we'll deal with scalar particles, and we'll deal with high spin particles, which usually look like a field with a bunch of spinor indices. So alpha, beta, up to gamma, which will denote the negative helicity degree of freedom of the field, and positive helicity fields will have a bunch of dotted indices. So that's the intuition. Let me just do the Maxwell case to give to tell you exactly how this decomposition into positive and negative helicity happens. So for scalar field, we'll of course try to solve the standard Klein-Gordon equation. So, and for the Maxwell case, let's see exactly what PDEs I can get by decomposing the Maxwell equations into its spinor components. So a Maxwell field, A mu, or AA in my notation that I was using, you can turn that into its spinor components. Just to remind you, I'll write this one last time. This looks something like, okay, I think I defined this with upper indices, but you can easily lower the indices if you like using Levi-Civita symbols. So with lowered indices, A alpha alpha dot just has some sign changes, but otherwise it's more or less the same object. X plus I bar. We're going to write field equations for objects like A alpha alpha dot. But instead of the gauge potential A alpha alpha dot, we're going to deal with the physical degree of freedom, which will be the field strength. And it will turn out that writing the field equations, okay, this is Maxwell, so just plain old QED. It will turn out that writing the field equations directly for the field strength will make the field equations look much more clear, and it'll give a form that will be much more easily generalizable to higher spin. So you have the field strength, which in spinor components, alpha beta, FAB, spinor components are alpha alpha dot, beta beta dot, which is twice the antisymmetrization of the usual field strength, but just written with respect to the spinorial derivative of the spinorial gauge field components. Partial alpha alpha dot is short for d by dx alpha alpha dot. Okay, now you might remember from the last lecture that as soon as you have a quantity, which is a two form, which is basically antisymmetric in its space-time composite indices, you can decompose it into its SU2 irreps. So this is exactly the same kind of behavior that the angular momentum displayed. In that case, we had m alpha alpha dot beta beta dot, and I decomposed it into a negative helicity part plus a positive helicity part. So I'm going to do the same for this object because it's also antisymmetric in its composite indices. Beta beta dot alpha alpha. And we can try, in the discussion session, we can try sort of doing it explicitly if anyone is interested. But otherwise, this is basically a representation theoretic decomposition. So you can take my word for it. So the decomposition in this case will be into a positive helicity field strength and a negative helicity field strength, where you can now find the explicit expressions. F alpha beta will be up to factors of 2 partial alpha alpha dot A beta alpha dot. And maybe I'll leave it as an exercise for you to check that this is symmetric in alpha and beta. So I told you in the last lecture, to get F alpha beta from this expression, you basically just contract with epsilon alpha dot beta dot, and use the symmetry of these objects to basically kill the contraction of epsilon alpha dot beta dot with F tilde. And that will extract F alpha beta in terms of this definition. In any case, now we want to see what is the spinor decomposition of Maxwell's equations for these helicity decomposed field strengths F alpha beta and F tilde alpha dot beta dot. That's the thing that will take a clean form. So Maxwell's equations say that partial alpha alpha dot. So in your usual tensor notation, it's that partial A FAB equals 0. And in spinor notation, you just replace A with alpha alpha dot, B with beta beta dot. You plug this in. You plug in the SU2 decomposition. And use the index raising or lowering. If you've forgotten how to raise a lower index, use your favorite convention. My convention was that if alpha and alpha are like slanted towards the right, then you can just lower it directly. So you would get partial beta lowered from this epsilon, alpha dot stays where it is, acting on F tilde, alpha dot beta dot. So now the alpha dots are contracted. Plus the other one you basically find by the same pattern. Beta dot alpha F alpha beta equals 0. So that's your Maxwell equation written in spinor form. You would think that I haven't really achieved much simplification yet, but now you would use the fact that the gauge field strength comes from a gauge field, so it satisfies the Bianchi identity. The Bianchi identity tells you, you can check this, maybe this you can take as a nice exercise. You can compute partial alpha, you can compute the difference of these two objects. And you can check that if you substitute this expression for F alpha beta in terms of the field, in terms of the gauge field, and the similar expression F alpha dot beta dot equals partial alpha alpha dot A alpha beta dot for F tilde, and you'll see that this basically vanishes. So this becomes a spinorial version of Bianchi identity. This is a very nice calculation. You should do it as an exercise. It's very simple, just plugging in that thing and then symmetrizing or anti-symmetrizing to show that this is basically 0. So this is your version of Bianchi identity. But once you have these equations in terms of the field strengths, you can forget what local gauge potential it gave rise to.
Can I ask you, sorry? Can we, for example, find the same Bianchi identity starting from the epsilon euro sigma, then you have ferro sigma?
Yeah.
And then you replace, every time there is a vector index, we replace it with the alpha dot.
Yeah.
I guess it works, no?
Yeah, exactly. It's just that I didn't want to say that epsilon ABCD has that decomposition.
But this is a general thing, because it's like saying that 1 alpha representation splits into alpha 0 times 0 1 alpha.
Exactly. Yeah, for massless fields, this happens to all higher spins as well.
Exactly.
So it's fairly general.
So many indices there are, and you replace with the pair.
Exactly. So you'll use some higher spin analog of the Bianchi identity.
This is just telling you that individual piece in this equation is 0, just add and subtract the things.
Yeah, that's what I'm.
Simplification, okay.
Yeah, exactly. So now I get. So this leads to the so-called spin 1 zero rest mass, which is shortened to ZRM usually in 1980s literature, free field equation. So if you read papers by Penrose, McCallum, or textbooks by Huggett and Todd on twistor theory, the name that you will come across is zero rest mass field equations, and basically there will be a very nice generalization. So okay, in this case you can add and subtract and you'll get the field equations partial alpha beta dot F alpha beta equals 0. That's the negative helicity field equation. Whenever I say negative, just think of undotted indices. That's my convention for a negative helicity object. And the positive helicity equation of motion is the other thing. Partial alpha dot beta F alpha dot equals 0. Sorry, F alpha dot beta dot equals 0. Tilde. So you see that there's a very nice and simple decomposition that now you can easily guess the generalization of to the higher spin case. Any questions about this derivation? If anyone is interested in that decomposition, I can tell you in the discussion session. Yeah?
Yeah, just maybe a small thing, but can you just run like, you don't pick up a minus sign when you do the raising and lowering indices on the Maxwell equation above?
Well, unless I did my convention wrong, I'll just repeat my conventions and maybe. So basically, if you have a raised index on a spinner, my convention is that that is lambda beta. And then for the index, and the inverse of this is epsilon alpha beta lambda beta, where I've used the convention that epsilon alpha beta epsilon beta gamma is minus delta of alpha gamma. So they're like, I put my minus in this inversion, yeah.
And the same for the dotted indices, right?
The same. Yeah, it's identical. I'm using the same convention for both the undotted and dotted indices. In the literature, like in Cerny's book or something, you might come across like different conventions for dotted and undotted. I do not know why that is useful. There must be some use, otherwise people wouldn't follow it, but I have never needed to. Okay, so that's that. The higher spin generalizations are now easy to guess. Can you tell me the generalization to the gravitational case, the spin 2 linearized Einstein equations case? So, firstly, if you have a spin J field, so I should say helicity if you are allowed J to be both positive and negative. So suppose you have a helicity J in Z over 2 field, massless field. Can someone guess from the scalar and the spin 1 pattern how many spinor indices I should put on my field? So suppose I have field strength. In the scalar case, I had no indices. In the gauge field case, for the positive helicity case, so J equals +1, I had 2 indices, 2 dotted indices. For J equals -1, I had 2 undotted indices. Can anyone guess the pattern?
2G.
Yeah, 2 mod J if you like. So when J is positive, then that's a positive helicity field, so you get 2J dotted indices. So let me just represent my potential by psi, my field strength by psi, and that will give you alpha 1 dot alpha 2 dot all the way up to alpha 2J dot. And if I have a negative helicity field, then I take a bunch of 2J undotted indices, about 2 mod J in this case. And of course it had to be 2J, it can't be J, you can't have a half an index. Anyway. A gravitino will have, so 3 half, right?
Yeah.
Yeah, so it'll have 3 indices. A 14 will have 1 index. Yeah, that way. And the generalization to the higher spin field equations will be, so this is why writing the field equations directly in terms of the field strengths is so useful. If you write them in terms of the gauge potentials, you'll have to use Bianchi identity and stuff to sort of bring the field equations into some nice forms. And at the end of the day, in terms of the field strength, the field equations just are generalizations of that pattern. You get greater than 0, you get partial alpha dot alpha psi alpha dot beta dot up to gamma dot equals 0, whatever the number of indices, and J less than 0, you get, or maybe I can number them if you like, alpha 1 dot up to, in the negative helicity case, the field equation becomes twice mod J. So for the case of gravity, it's interesting to give you the physical interpretation of the field strengths. in the case of gravity, the field strengths are, can anyone guess what the field strength should be in the case of gravity? Exactly. So since the Riemann tensor vanishes on shell, the remaining Einstein and Bianchi conditions impose field equations on the Weil tensor. The Weil tensor is the only non-zero part of the curvature, the Riemann curvature, that you have to constrain by some field equations. Things that are zero are already constrained to be zero anyway. So in the case of gravity, yeah, that's the last case I'll sort of write down because it's nice. So recall that the Weil tensor, you can take the Riemann tensor and you can decompose it into a trace-free part, I guess. So this is the trace-free and one more condition which I forgot. Plus, there's a bit about the Ricci. There's a bit that depends on the Ricci tensor, which vanishes on support of the Einstein equations. And there's a bit that depends on the scalar curvature. The Weil tensor is the only thing. It has the same symmetries as our ABCD, the same Bianchi identities on shell. So it is the only thing that actually remains in the game, and then it has to satisfy whatever remaining field equations there are. So what one does is one writes C, A, B, C, D in spinor components. And if you open the book by Robert Wald, you will find this decomposition. So epsilon, alpha, beta, gamma, delta, psi, alpha dot, beta dot, gamma dot, delta dot, plus the other way around. So these will be, usually Weil tensor field strength are denoted by capital psi. But they are just the spin 2 versions of my little psi there. So the equations will be, so Einstein, linearized Einstein field equations, linearized Einstein equations, plus Bianchi. I suppose in this case, a linearized Bianchi, I don't remember exactly, will impose partial alpha, alpha dot, psi, alpha, beta, gamma, delta equals 0. That's the negative helicity condition. And the spin plus 2 condition is, the helicity plus 2 condition is that. So I'm gonna, whenever I have a graviton, I'm gonna denote it with 2 minuses or 2 pluses. This is useful in labeling operators in celestial CFT. But yeah, these are the equations. We're going to try to solve these using some integral formulae that we build out of twistor data. Yeah.
These arbitrary spin J things, do they also keep symmetry in all of the indices? So, for example, these psi's, are they symmetric under alpha, gamma, delta?
Yes. Thanks for the question.
And
they're all symmetrized.
I'm guessing then it's symmetries of the Weil tensor that mean you only get these two terms, because if you were just like expanding out tensorally, you could imagine, some epsilon alpha gamma, epsilon beta delta contribution.
Yes. So it's basically the symmetry that allows you to contract with epsilons and extract out just psi or psi tilde. Anyway, this is all 1980s simple calculations. You can go to these Royal Society publications, papers from JSTOR, and read about how these equations were derived by Roger in some very complicated potential formulations. And this is all the reduced at the end of the day. Did you know that there is a third potential in gravity, or a pre-potential for the metric itself shows up when trying to solve these equations? You can try reading Roger's paper on linear field zero-rest mass field equations in flat space.
The potential is for what? Sorry,
Huh?
it's for what, the potential?
It's a pre-potential for the metric.
For the metric?
Yeah. I don't know how general an object it is. It certainly exists in the self-dual metrics.
Okay.
Yeah, but it's or for in the linear field theory. Yeah, the metric is the pre-potential for the connection. The connection is the potential for the curvature, but there's a potential for the linearized metric perturbation that certainly exists. Okay. So now we want to solve for these equations. So I'm going to do that in terms of. So since Prahar's lectures, I have realized you're a bit more comfortable with mathematics than I was afraid of. So I'm just going to use a little bit of cosmology. Actually, not really. I'll just say some words. Okay. So what I'm going to do is I'm going to map holomorphic data. I rubbed my slogan off, but I'm going to map some holomorphic data from twistor space through some integral formulae into some data on space-time, into these field strengths on space-time. So in this sense, one can think of there being a duality between some field theory on twistor space whose fields are these holomorphic data, and there is some correspondence with the space-time fields. So let me write down this in some simple cases. So to define, so this is section 3.2. I probably didn't title that one, but this whole thing was 3.1. Penrose integral formally. So Penrose integral formula consists of, basically you first take a differential one form on PT. So take phi. It's a differential one form on PT, but of a very specific kind. It's a so-called not one form. So remember, my twistor coordinates on PT were z's. They are complex coordinates on C4 before I projectivize. I'll denote their complex conjugates by z bar, a bar. This is literally just complex conjugation, but at the level of components, I'm going to write this as mu bar alpha, lambda bar alpha dot, by thinking of complex conjugation as mapping dotted indices to undotted indices. But otherwise, this is just component-wise complex conjugation, nothing deep going on there. So these are my holomorphic coordinates on twistor space PT after holomorphic homogeneous coordinates. And these are the anti-holomorphic ones. So now, take one forms that are in the spans of the differentials of the anti-holomorphic coordinates with some functions, some smooth functions of z and z bar, but pointing only in the anti-holomorphic directions. So this is phi of z bar. It doesn't need to actually consist of holomorphic coefficient functions. The functions can have z bar dependence, but they need to satisfy certain conditions. Firstly, they need to be projectively well defined. So I don't want to go too deeply into why this mathematical condition is required, because the condition itself is very simple. It says something like there's a vector field z bar a bar d by d z bar a bar that generates scalings in z bar, and this differential form should be orthogonal to this vector field that generates scalings, because this vector field points off the quotient of C4 by the C star scalings. So I'm just going to say that this differential form acts trivially on this vector field, which is basically just saying that the contraction of z bar a bar with the a bar index of this FA these coefficients is 0. So this just says that the differential form, did I say not one form? Okay, yeah. This is a not one form, 0, 1 form. And this condition says that it's defined on the quotient. So defined on projective Twistors space. Technically speaking, it's a section of some bundle, but we don't need to think that hard. Just think of these as some functions on C4, smooth functions which satisfy this condition that are orthogonal to the vector Euler vector field. That thing is called the Euler vector field that generates scalings. And the next condition is that it be homogeneous. I promise you, I'm not just putting conditions randomly. We will get somewhere with these. Next condition is that this differential form have a definite homogeneity. So we want something like phi of under scaling Sz as conjugate, Z conjugate. It should have a definite scaling weight. And now I'm going to assume that its scaling weight is related to the spin of my space-time field. So I'm going to take the scaling weight to be minus 2j minus 2. And I'm going to assume that it has 0 scaling weight in the complex conjugate. This might remind you of the condition of a function being conformal primary on a Riemann sphere CP1. This is basically a generalization of the conformal primary condition from CP1 to CP3, but now, of course, we're looking on PT, the open subset. And
sorry, I'm missing the minus 2. Why is there a minus 2 there? Which conventions?
Yeah, once I fix the conventions for how I label spin, it's sort of fixed.
Sounds like a scalar, not a transform.
No, a scalar transforms. The spin-1 gauge field doesn't. Anyway, yeah, it's there because I'm going to integrate on certain Riemann spheres that I defined last time. So the last condition on this data, so you think of these as some fields of Twistors space which will generate data. Someone asked a question? No. You're thinking?
Yeah.
Okay. Cool. The last condition and the most important condition is holomorphicity. Holomorphicity, so holomorphic functions are defined by the Cauchy-Riemann equations. So if I had a holomorphic function, don't write this down, this is just to remind you. If I have a holomorphic function f, then it would be holomorphic if it's annihilated by d by dz bars for all the z bars. That's holomorphic functions. Holomorphic one forms are defined by a generalization of this. To define holomorphicity for differential forms, you first take your exterior derivative, which in these coordinates looks something like this: dA plus d bar z bar dA bar, where dA is my short for d by dz, and dA bar is d by dz bar a bar. Okay. Since we have complex coordinates, we have very natural decomposition of the exterior derivative here into a part that increases only the dz, the amount of dz's that occur in your differential form, and a part that only increases the amount of dz bars that occur in your differential forms. We are going to take just this object because this is now a geometrically well-defined object. It's well motivated. This is called a d-bar operator. So d-bar is defined as dz bar a bar d by dz bar a bar. And it also goes by the name of a Dolbeau operator in complex analysis. The idea is that first check how this acts on functions. Does it give us the correct holomorphicity condition on functions? And indeed it does. If you have a function, suppose we impose d bar f equals 0. It's called d bar or del bar, whichever you prefer. And this would impose that partial f by partial z bar a bar d z bar a bar equals 0. So component by component, it would set the anti-holomorphic derivatives of a function to 0. So holomorphicity with respect to d bar is consistent with the Cauchy-Riemann. Now we know how d bar will act on differential forms. So that's how we define a holomorphic differential form. So phi is holomorphic if d bar phi vanishes. You compute this. This will give you, by the usual rules of exterior derivatives, partial f a bar by partial z bar b bar d z bar a bar wedge d z bar b bar equals 0. The antisymmetry in a bar b bar will then tell you that partial f a bar partial z b bar should be, so in some sense some kind of curvature should vanish. So let me rub that off.
So are the sections of a flat of a three-move bundle, or sorry, of a flat different connection?
Yeah, so no. They're just differential forms. They're sections of certain bundles with definite homogeneity. Yeah. Yeah, holomorphic functions of definite homogeneity. So ON in the line. Yeah.
And the bundle is three-move curvature, so
You don't really care about the putting any metric on the bundle, but usually you would put Fubini 2D and will have some curvature. But the point of twistor theory is that we never use the notion of a metric on twistor space or any of its bundles. The entire notion of space-time fields that depends on space-time metric and stuff is translated into complex analytic geometry. So now I'm going to show you that things like eta AB dA dB phi, an equation that depends on the space-time metric smooth differential geometry, is going to translate into d bar space. I call this kappa phi equals 0, where phi has homogeneity -2, so weights -2 and 0 if you like. Anyway, so let me just finish that. The holomorphicity condition is that dA bar FB bar equals dB bar FA bar. So let me just collect all the conditions. That's one condition. The other condition is that it points along PT and along the quotient. And the last condition is that the overall differential form scales like that. So it's a bar. So suppose our differential form satisfies these conditions. Exercise prove that, we have to do case by case. So suppose j is less than 0. This is the easiest case. Not 0, but less than 0. In this case, the field strength of a negative velocity field negative velocities are undotted indices, is constructed by this beautiful integral formula. D lambda wedge phi which phi am I using? I'm using bar phi. Okay. Phi, and you integrate this along Lx. Anyone remember what Lx was from the last lecture? Lx was my twistor line. So last lecture I showed you that you can embed for every point x in Minkowski space, you can embed a Riemann sphere or half of a celestial sphere into twistor space given by the linear equations, the linear embedding mu alpha dot equals x alpha alpha dot lambda alpha. That's Lx. And all I'm doing here is taking my phi, restricting it to this Riemann sphere Lx inside twistor space. You'll have some twistor space here. you'll have some Riemann sphere corresponding to the point x. Take your phi, restrict it to this Riemann sphere, and then integrate it against the canonical volume form, the canonical holomorphic volume form on the Riemann sphere. The canonical holomorphic volume form in homogeneous coordinates, lambda alpha, happens to be d lambda equals this contraction of lambda with d lambda, which in components looks something like lambda 2 d lambda 1 minus lambda 1 d lambda 2. So this happens to just be the most natural thing that you write. If you're uncomfortable with homogeneous coordinates on the Riemann sphere, you can very easily turn it into affine stereographic coordinates by basically going to a patch. So in a patch on the Riemann sphere, you set lambda alpha to be 1 comma z, 1 comma little z, if you want to think of it as a celestial sphere of some sort. So you set lambda alpha equals 1 comma z if you like, and then lambda 2 d lambda 1 minus lambda 1 d lambda 2 reduces to minus dz. Sorry about the convention. If you set it to z comma 1, it gives you dz in the other patch, and the change in sign is expected because you're changing orientation when you look from above the sphere or below the sphere. Anyway.
Question? Maybe nothing else. How do you get J indices on?
Oh, sorry. I completely forgot about. Yeah. Sorry. Thank you. I forgot about half the formula because I thought I should draw the diagram. The J, can you tell me how do you get two J undotted indices? What is the natural object in the game which has these indices? The only object which has these indices? The lambdas. Just plunk down lambda alpha 1, lambda alpha 2, up to lambda alpha 2 mod J. And now this you can show. The theorem is that this object solves the linear field equation. So solves partial alpha dot psi alpha 1 up to alpha 2j equals 0. So if I try showing this to you in class, I'll probably get it wrong. I'll do a simpler case just to motivate, depending on how much time I have. Let me see how much more I have. Maybe I can do momentum eigenstates in the 6th lecture. Okay, so we can do I should show you a simple example. So we can take the special case where phi only points along the Riemann sphere directions. So suppose we work out the special case where phi looks like this: f alpha dot d lambda bar alpha dot. This is the easiest case to work out. It works out very quickly. It can depend on z and z bar in an arbitrary way. Now, the condition that z bar, a bar, f a bar vanish, in this case becomes lambda bar alpha dot f alpha dot vanish. Because of this condition, what's the quickest way to motivate this? So that condition is actually naturally imposed if it's actually uniquely imposed if f alpha dot is proportional to lambda bar alpha dot. Basically what happens is that if f alpha dot is proportional to lambda bar alpha dot, then of course this is true because lambda bar contracts into itself and vanishes. But you can also expand this into components and show that this is just saying that lambda bar 1 dot f1 dot plus lambda bar 2 dot f2 dot equals 0. So f1 dot and f2 dot have to be proportional to like just parallel lines condition. So I'm just going to say that f alpha dot equals lambda bar alpha dot f for some function of z bar. This satisfies our conditions as long as it has the correct homogeneities. So you get something like, I'll take a minus here just for convenience. So I'll raise and lower indices and make it look nice. This object is denoted d lambda bar, just like I defined d lambda to be lambda alpha contracted into d lambda. That's just convenient notation. If you plug this in and assume that phi f, okay, now I have two more conditions. I have the condition that f has some definite homogeneity. Now that's just a function. Homogeneity is easy. Okay, I don't need to write the homogeneity again, just assume it has homogeneity minus 2j minus 2. And holomorphy is the non-trivial condition. Holomorphy says that d bar f equals 0. Now, d lambda bar. If you expand this holomorphy constraint, what do you get? You get partial f by partial mu bar alpha, d mu bar alpha wedge d lambda bar is partial f by partial lambda bar alpha dot d lambda bar alpha dot wedge d lambda bar equals 0. So all we need is this component of the condition. You can actually show that this component is secretly trivial because of homogeneity properties of f, but we only need to set this component of d mu bar which d lambda bar to 0. That will actually be enough for the sake of this example. So keep in mind the condition that f is holomorphic in mu alpha dot as a function. With this condition, we can actually show that the Penrose integral formula works. So you basically take partial alpha alpha dot psi alpha 1 dot alpha 1 alpha 2. So maybe I'll do the Maxwell case because I don't want to write down loads of indices again and again. So for the Maxwell case, the formula looks something like f alpha beta of x equals the integral over Lx of d lambda wedge lambda alpha lambda beta times that example differential form f d lambda bar. Now I restrict to the line. The line is just mu equals x dot lambda. So this becomes f as a function of mu equals x lambda, lambda, and lambda bar. Now it's only a function of the combinations x lambda and lambda bar. Once you have this property that f is only a function of x times lambda, checking that f alpha beta satisfies the appropriate field equation becomes super easy. You get d lambda, d lambda bar, lambda, lambda. So we have a lambda alpha here. Let's take it and contract it into this derivative. Okay, sorry. Alpha is contracted into alpha, so alpha goes there. Now I'll just keep alpha dot upstairs. That doesn't matter. So you have partial alpha, alpha dot, acting on f, x lambda, lambda, lambda bar. Now, can someone tell me why this vanishes? Why does lambda alpha, partial alpha, alpha dot of a function that depends on x only through x beta beta dot lambda beta, why is this 0?
Lambda alpha and
Exactly. So basically you just do chain rule. This tells you this is lambda alpha partial alpha alpha dot acting on this combination. It will of course not act on lambda lambda bar. I'm taking a position derivative. Just get x beta beta dot lambda beta d by d mu beta dot f x lambda. And partial alpha alpha dot acting on x beta beta dot gives you delta beta dot alpha dot, which makes you contract lambda alpha with this lambda beta and kills this term. And so henceforth lambda alpha d alpha alpha dot f vanishes. You can pat yourselves on the back. We have landed the spaceship. Now, any questions about this derivation? This was just supposed to be an example. The more complicated case, we can do it as an exercise if anyone is interested, or you can just go home and try doing it yourself. It's fun. Or maybe you can take this as a motivation to read Roger's papers. Any questions about this general formalism?
No restriction on the line was, I mean, obviously, in that case you restrict it to, there's a way to introduce x, you restrict and then it works, no?
Exactly.
If I restrict in any different way apart from the line, or just because any...
This is the only combination that is naturally annihilated by this operator, but maybe then you have to find...
You have polynomials in the...
Yeah, it's just that the fact that it's annihilated by that operator has a nice geometric interpretation that f, or this differential form, is holomorphic on twistor space. That's the kind of geometric interpretation that Penrose wanted back in the day. And that is the kind of geometric interpretation that has sort of transformed space-time data, PDEs that depend on the metric of space-time, into just Cauchy-Riemann type PDEs on twistor space that say that d bar of this differential form bar phi is 0. So we have transmuted differential geometry into complex geometry. You're very happy because complex geometry is holomorphic things are like, if you're just saying give me something holomorphic, that's sort of easier to give than saying give me a solution of some PDE. Even if it's a linear PDE, you have to impose boundary conditions and construct stuff. Anyway, the real power of twistor theory, of course, is that there are ways to generalize this Penrose transform to certain nonlinear PDEs in the self-dual sector. I will not discuss that because that requires a lecture of its own. But you can take these methods and then you can go ahead and try to find fully nonlinear solutions of the Einstein equations with the property that are sort of self-dual, that they have half their Weil tensor 0, or in the gauge theory case, half their field strength 0. And so you can, in some sense, take account of interactions of quantum field theory as well. We won't discuss this here. We'll see examples to scattering amplitudes maybe tomorrow. I don't know if I have... Oh, let me just write down the positive helicity case, and then we can maybe take a break. The positive helicity case is very easy. Just the integral formula now requires dotted indices. And so this is a fairly natural guess. Actually, now maybe you see why the scalar case had to have homogeneity -2. I think I forgot to say this, but the homogeneity condition is required because that integral is an integral over the Riemann sphere, but I have written it in homogeneous coordinates. And for it to actually give a genuine integrand on the Riemann sphere, it has to have homogeneity 0. If phi has homogeneity -2j -2, -2 mod j -2 actually, then that thing just... this is basically the same thing that you do in CFT to check that your conformal integrals are well defined. If phi has homogeneity -2 mod j -2, this object has homogeneity 2 times mod j, and this object has homogeneity 2. So the total homogeneity cancels, and the integral is a well-defined conformal integral over the Riemann sphere. In the positive helicity case, you take the same object, it's just that now you don't need to have any absolute values. This scales as -2j minus 2. Again, the same condition that phi is d bar closed. And the integral formula for a positive helicity field strength now turns into integral over the twist line d lambda wedge. Now you need dotted indices. It turns out that the correct thing to do is to take holomorphic mu derivatives. And this genuinely you can take as an exercise to do at home. You take a bunch of holomorphic derivatives of phi. Of course, when I say derivatives, you view these as just acting on the coefficient functions of phi. I've just written them like d by d mu's, but they won't act on the dz bars anyway because these are holomorphic derivatives. Take these derivatives, restrict to the twistor line, and then you can show that this gives rise to a field that satisfies the required field equation. And that's the magic of twistor theory. If you have a scalar, then you basically just write down phi equals integral d lambda wedge bar phi restricted to Lx, and this will now solve the Klein-Gordon equation on complexified Minkowski space. All right. Do we want to take a break now?
Yeah.
And we can do the next lecture. This is all classical.
And so far, I know you're setting the.
Right.
I know you're setting the stage for later things, but what